Hi class, we are now beginning the last portions that we're going to cover before the end of the semester. So we are going to go over what is called the Laplace Transform. So the Laplace Transform is real useful. It'll take us a little bit to get used to, but it's very, very useful technique and method that we'll go over right now. So let's go ahead and get started. So the Laplace Transform, this basically allows us to take a differential equation problem and turn it into an algebraic problem. Okay, so the transform actually consists of an integral. Okay, so remember that integration and differentiation, they are transformations. If I plug in an integral, or I'm sorry, if I plug in a polynomial into a integral, I'm going to get out a completely different ordered polynomial. It transforms my polynomial into a higher order polynomial. If I plug my polynomial into a derivative function, right, the function of the derivative, it will turn it into a lower degree polynomial. Okay, if I plug in, let's say, a rational function, 1 over x, for instance, into the integral function, then I get out a natural log function. It gives me a new function out, right? So an integral is a transformation. It's a type of transformation. If you guys are taking my linear algebra course or have taken a linear algebra course, you should have seen something somewhere about how differentiation and integration are what we call linear transforms. Okay, they work in a linear method and they transform your function into a brand new function. Okay, either of the same type or a different type. So that's what we're doing. The Laplace transform is an integral transform. It's a type of integral transform. Right? So what we do is we take a multivariable integrand or integral. Okay, so we're going to have two variables in our integral, but we're going to hold one of them fixed constant. Right, so when we integrate, we are fixing one variable constant, and we're integrating with respect to whatever variable it is that we're actually working with. And what we're going to do is our integral is going to be bounded. So what we're going to get out then is a function in our new variable, right? So it actually changes the variable as well, right? So what we're going to do is we're going to change the variable by having multiple variables and holding one of them constant. Okay. Now I said that the integral is going to be improper, or I'm sorry, I said it was going to be bounded. It is bounded. It's bounded on one end and it's bounded by infinity on the other. So we're going to do an improper integral. Okay. If you don't remember what an improper integral is, then I suggest you just go back through your calculus book. It would have been one of your integrating methods in calculus 2. It's basically when you go from a bound to infinity, or from negative infinity up to a bound, generally from 0 to infinity. And we're just really interested in whether or not this integral converges or not, right? If it converges, then it converges to a value. There is an actual sum. If the integral does not converge, then you basically have an area of infinity under your integral, and you can't really do anything with it, right? So we need to have a few certain properties going on with our integral, right? With our functions. So to create an algebraic function, we're going to, again, do a multivariable integral. We're going to hold one variable constant. And what it's going to do is going to give us a change of variable linear transform. I'm going to go from one variable to another. So that's our change of variable. And I'm doing that by a multivariable integral, where I hold one of those variables constant. Okay, so that's a lot of talking, but let's see how this works. Okay, so let's talk about the definition, and then we'll get into some examples. Right, so let's say that we have a function that's defined from 0 to infinity. Okay, which is important because this is the bounds that we integrate over for our improper integral. Okay, here we're going to use a variable of t. We could use x, right, but generally for these Laplace transforms, standard notation is t. These are things that change over time, right? So our integral then our change of variable integral, right? Our change of variable linear transformation looks like this notation, okay? So this fancy L is for the Laplace transform. So the Laplace transform of our function is going to be an improper integral from 0 to infinity of this exponential e to the negative st, right? So here s is a variable and t is a variable. T is the variable that we integrate across. S is the variable that we hold constant. We're just going to consider this as being some constant for right now during the integration portion. That way what happens is we get out a new function that is a function in terms of our new variable s. Okay, so I'm doing an improper integral. S is a variable, t is a variable, but while we are doing the integral, we hold s fixed like a constant. So then that way when we integrate against t and we evaluate it at the different bounds, right? Remember, if you evaluate an integral from one bound to another bound, you get out a single value. You don't get out another function. So the t portion of this bounded integral means that we get, it kind of just goes away and it transforms into a new variable now, which is the s variable, okay? So this is called the Laplace transform of our function f of t, okay? So of course that function has, or I'm sorry, not the function, but the interval, right? This interval has to converge, okay? And you're not going to run into anything, I believe, through this whole chapter where something doesn't converge, okay? So it converges because of this exponential term here, right? So note that s is the variable that we're holding constant, so that when we do this Laplace transform of our function, we're going to get out a function in s, okay? S will be the new variable, right? Integrals are linear transforms, as I said before. So we're just going to show this, okay? Property, they're linearly independent. That's what it means to be a transformation. We've talked about this a little bit. We've definitely talked about the linear independence. So basically, if I have two constants, okay, alpha and beta, they're just constants in R. They can be any value, pi, square root of 3, 2, 1/2, negative 103, doesn't matter, right? They're just some number, okay? They don't have to, they just can't be imaginary in this case. So let's say we have function f and t, okay? So we're going to take the Laplace transform of f and the Laplace transform of g. But while we take this transform, we're going to multiply these functions by these constants, okay? So the way that the Laplace transform works, since it's a linear transform, it's an integral, okay? So if I took the integral of some big thing separated by a plus sign, I can separate that integral into two parts, okay? Remember, this is just an integral, right? So the properties of integrals apply to this Laplace transform. So if I had one integral against a function, a polynomial for instance, I could just integrate each term in the polynomial separately. That's how we do it. So the Laplace can be separated into two different transforms. If you have a constant in your integral, you can pull that constant term out to the outside and then do your integration on your function. So that's what we would do here, okay? We can pull out that we can pull out that constant term, and then we get the transform for the Laplace of f and the Laplace of g, right? So that gives me big F and big G, both in terms of s, times these constant coefficients that we were able to pull out, okay? So the Laplace transform of alpha f of t plus beta gt will give me a, or alpha times that transformed function plus beta times that transformed function. All right, so let's go ahead and do an example, right? So let's evaluate the Laplace transform of this big old long function, okay? So 2t squared minus 4 e to the negative 9t plus 3 sine of 2t. Now, remember what the Laplace transform is, okay? It's an integral from 0 to infinity, e to negative st. S stays as s. It doesn't change into 3 or 5 or something like that, right? Times my function. And remember, it's an integral, okay? So I'm taking an integral of a big long thing, which means that I can break this down into pieces. So instead of doing one long integral, we're going to break our transform down into pieces, okay? So I have the Laplace transform of this function, okay? So that's going to be the same thing as me taking the Laplace of just the first part and pulling out that constant. So I'm really just doing 2 times the Laplace transform of t squared. Again, I'm going to apply this linear transform property that we have, right, against each separate function. So I'm going to take this and I'm going to rewrite each function in this middle form. Pull out the constant, transform of the function, plus pull out the constant, transform of the function, right? So we're going to do this slowly. Before I would just give you a full line, so I'm trying to do things a little differently here because I know you guys are writing notes as we go. So we're going to kind of pop one thing in at a time so you have time to write things down as we go through it. Okay, so this first part, I can pull out the pull out the 2, transform t squared. Okay, the next one I'm going to do the same thing. I'm going to pull out the minus 4 and I'm going to Laplace transform e to the negative 9t. Right? Kind of get where we're going here. The next one, what do I pull out? 3. And what's left on the inside? The basic constant one. Okay. Here I'm going to pull out 2. No, I'm going to pull out 3, right? Pull out 3. The function left over, sine of 2t. Okay. Hopefully that didn't trip you guys up there. So this is what I write my transform as, right? Pulling out the constant, and I'm doing several transforms at once on each one of these functions that I have that make up my single function, okay? Now we have to write these as integrals, okay? Because remember, this transform means I'm multiplying t squared times e to the negative st and taking a bounded or an improper integral. Same thing here, same thing here, same thing here, okay? So this first transform will look like this. My constant is pulled out. The Laplace transform means I have an integral from 0 to infinity, e to negative st, right? That's that the portion that helps me transform into a new variable times my function t squared, okay? This will be the same thing, negative 4, improper integral from 0 to infinity, e to the negative st times e to the negative 9t, okay? I do that with my next one, pull out plus 3, integral of just e to the negative st, right, times 1, so it doesn't do anything. Same thing here, I pull out a plus 3, do the integral from 0 to infinity of e to negative st times sine 2t, okay? So, live integration going on, right? I have 1, 2, 3, and this makes 4 integrals to do, right? Some are easy, some are a little bit harder, right? This one will not be too bad at all either, right? Because I have the same base, I can add this to a single base and add the exponents, right? This is 2 functions times each other, 2 functions times each other. That means I'm going to have to do a little bit of integration by parts for these two because I have 2 functions multiplied in my integrand, okay? So let's go ahead and work on these things one at a time, okay? So let's work on this first one. Now, sometimes I'll write the integral again, sometimes I won't. We're just going to kind of work things out, right? This is a function times a function. It does not simplify too well, so we have to do integration by parts. So hopefully you guys remember that when I do integration by parts, I do not stick to the formula. I hate that formula. I don't teach it that way in my Calc 2 class, right? I do the table method. So one of the functions we differentiate, the other one we integrate, and then we change signs, plus minus, plus minus, plus minus, and then we kind of do this diagonal multiplication thing. Now the one I want to integrate over and over is the one that will go to 0. If I have a function that disappears, that's the one I want to differentiate, right? Because eventually I'll get to 0 and it goes away. Over here we're going to end up doing the same thing, but if you notice, e to negative st never drops down in power. This never drops down in order either. So when I come to this, we do something a little bit different. Maybe you remember how it works, maybe not, but we'll talk about it when we get there. Okay, so here when we do integration by parts, it's kind of recursive. So again, here nothing disappears. So we got to do this a little bit differently than what we do here. Okay, I haven't showed you guys this before yet, but I'm sure you can figure it out from previous experience. Okay, but we have seen this quite often. So I'm going to differentiate t squared because it differentiates to 0. The e, I will integrate over and over, and it will not disappear. So for the first setup, we have, so the way that this works is I can't do one column and then the next column and then the next column. I can only go one row at a time. So, so the first thing we have is t squared here, okay, and the next is the one that we're going to integrate, right? I'm going to continue to differentiate here, and I'll continue to integrate on this side, okay? So t squared to t to 0. This one is the e to the negative st. When you integrate, you pull 1 over the value we're holding constant, which is s, right? So we're considering s a constant here. So if this was like e to the negative 2t, this would be negative 1/2, and then times a negative 1/2, and another negative 1/2, right? But it's not a 1/2, it's a constant, in this case, of s. So the order just keeps going up by 1, and we alternate from positive and negative. The t squared connects to this one. Again, it's just a formatting issue thing here, you guys, right? But the first one connects with the second one over here. So t squared goes to this term. This 2t goes to the next term. This 2 goes to the last term, right? So I multiply, I multiply, I multiply, and then I multiply by this sign here. So t squared times negative 1 over s times a positive. So this will be a negative. 2t times 1 over s squared, e to negative st, times a negative, right? Positive times a negative, so this term will be negative. So one at a time, I get a, because I'm multiplying by 2 here, that's where this 2 comes from, right? 2 times L t squared. So 2 times t squared, 1 over s, so 1 over s and the 2, e to negative st, right? The next one also times 2, so I'm going to have 2 times 2 is 4, over s squared times t, e to negative st, okay? Then one more 2 times 2 is a 4, over a negative s cubed, e to negative st. And that's my integral, right? So you're just multiplying down the columns, and then again, don't forget to multiply by 2 here, because this is 2 Laplace transform of t squared. So this first term gets transformed in this way, right? But we have a problem here. I'm not done, you guys, right? Because I need to evaluate this from 0 to infinity. I still have t's here. T is everywhere. My transform needs to turn into just s's. So we're going to evaluate from 0 and infinity. All right, so now let's think about this. Okay, remember, you evaluate at the first term, the top bound first minus the low bound. So as these go to infinity, you're really taking a limit here, right? But we're in differential equations. We don't have to take limits. We can just think about this, right? So t squared goes to infinity as t gets large, okay? E to the negative st is an exponential. It's a decreasing exponential function. So now it's kind of a race, right? We could do L'Hopital's rule, take the limit of this and then do the derivative times one times the other. We don't have to do all that, right? Which one grows faster? Does t squared grow to infinity faster than e to the negative t grows to 0 or decreases to 0? Which one goes faster? Well, you should know that exponentials grow faster than power functions, right? So this, when evaluated at infinity, whereas we say as t gets large, the e function dominates this squared function. So this is going to go to 0, okay? Same thing here. E to the negative t goes to 0 faster than t goes to infinity. So this is going to be 0, this is going to be 0, this is going to be 0. So at the infinity term, we are going to have 0, okay? Then we're going to subtract what happens at 0, okay? So at 0, this goes to 0, so this whole term is 0, this whole term is 0, And then what happens here? We get e to the 0, which is 1. So I got 0 minus a minus 4 over s cubed. Okay, which gives me positive 4 over s cubed. So the 2 times the Laplace transform of t squared gives me this function, 4 over s cubed, right? That is the transform of 2 times the transform of t squared. Okay, so that's your first transform. Now we have to do 3 more of these. Okay, so for this next one, we have e to the negative 19. So again, remember we can, we looked ahead a little bit. We can combine bases. Okay, so I have this integral. I pull out the negative 4 already. I'm going from 0 to infinity. E to the negative s plus 9t, right? Combining this base and pulling out the common negative term. So we already see what it looks like when we integrate exponential functions. So we know this is just going to turn into something in the denominator. Okay, 4 over s plus 9 with the minus, and the minus that's already there, so now it's positive, times, again, the exponential already. We're going to evaluate from infinity to 0. So plugging in infinity here, this is going to go to 0, right? This is a negative exponential function. This is going to go to 0. Minus, and when I plug in 0, this part goes away. And I have the 4 over plus 9. So I have this, which gives me negative 4 over s plus 9. So this is our next Laplace transform in our function, right? So now we got 2 left. Okay. Again, I hope you guys are writing these down, because I only have so much room to work on before we go to a new screen, right? So we can get one more in here before we have to do this on a completely separate screen. So for this one, now it's the same thing. This is my integral, which is super easy to do compared to like the first one. Okay, the second one was pretty easy. This one should be even easier because it's just negative s to the t. We already know what that's going to look like. It's going to look like this, times 3 from evaluated from 0 to infinity, right? So negative 3 over s from infinity to 0. Okay. Sorry guys, this should be e to negative st should still be there, right? But we know what's going to happen. It's going to do the same thing. Okay. So we have 0 minus 3 over s, and I'll fix this in the write-up, you guys, but the math is fine. The only thing we're missing is the integral part. But we saw from the last example exactly what happens. It just, the constant is what matters the most, right? So I'm going to get 3s for this because it's very, very similar to what I had for this one, right? So now I have my first 3. I have 4 over s cubed, negative 4 over s plus 9. I have 3 over s. And then now we have to do this one, which is very similar to the first one we did, but slightly different. Okay, so let's talk about this. Same thing. We're going to set up our integral. We're going to set up our table of values. Now, remember sine is cyclic. It goes sine, cosine, negative cosine, back to sine, right? It goes in fours. E, this is just going to follow this pattern forever. So when I want to integrate and when I want to differentiate, it kind of matters which one I put where, right? But the e is the one we really want to just keep integrating, okay? The sine function is the one we're going to differentiate. So we're going to differentiate until we get back to one of the sines. We're not going to go through the full cycle of options for sine. We'll just go until we get sine again, and then we can do some fancy stuff, okay? So this is my table, and as you notice, this one never goes to 0. Now, what you didn't notice here, okay, which I haven't been writing, is that this last term, once you get to your last term, these two actually multiply together. But since this is 0 and it multiplies against this, it goes to 0. So I only had to do the diagonal parts to write this. For this term, since it doesn't go to 0, I will have to multiply these last two terms at the very end. Okay, so I'm still going to go sine of 2t times this thing, 2 cosine of 2t times this, and then this part here where I multiply these last two, I throw that under an integral, or behind an integral. Okay, now to keep things simple here, I'm not going to apply this 3 yet. I'm really just looking at the Laplace transform of sine 2t. As you can see here, I'm not including that t, I'm not going to multiply by 3 until the very, very, very end. Okay, so if you're like, your math is off, it's because I'm not using the 3 yet. I'm only doing the Laplace transform of sine of 2t. So right now, okay, for this, I'm just doing the integral part. I'll leave this constant out because including it into the integration is just extra crap I don't have to worry about right now. I'll just do it at the end, right? So for right now, I'm just going to do this integration, okay? So that's what this is coming from. So that is going to give me the integral from 0 to infinity of e to negative st sine 2t, which is what I'm doing here with this table method. I'm going to get each of these diagonal products, right? So negative 1 over s times sine 2t, e to negative st is first, okay? Then the 2 cosine 2t times 1 over s squared e to negative st is second, okay? And my last one, now that I'm at the bottom, okay, and it's not 0, I have to multiply these two together, and it will be behind an integral, okay? So 4 and 1 over s squared, remember those are considered constants. The function parts are sine of 2t, and the exponential, okay? So I'm going to pull out the constants, and that is my integral, okay? So now what I'm going to do, right, is notice that this integral is the exact same as this integral, okay? The order is a little different just because of the order I decided to multiply them in, okay? But I have a sine 2t, e to negative st, e to negative st in terms of t, right? So what I'm going to do then is I'm going to take this entire integral and I'm just going to add it to the other side of my equal sign, okay? So I move this over with its buddy. The other side of my equal sign stays the same. I'm not going to combine these functions. I'm just going to leave them the way they are. I can start to simplify, but it's not necessary, okay? So for the Laplace transform, you don't have to do a lot of simplifying. You can just keep things as ugly as you want to keep them, okay? So I have my first term and I have my next term, okay? Now what I want to do is I want to combine these. I basically have one of these plus, because it's the other opposite sign of this when I move it over, 4 over s squared of these, right? So I'm adding common things together. So 1 plus 4 over s squared is going to be really s squared over s squared. So this is 4 plus s squared over s squared for a common denominator, okay? I have that many of these integrals. Remember, s is a constant term right now. It is it's a fixed variable. It's a value. It is not something that's changing in this case, okay? So I've added the things like terms together. Second sign, the right side of my equal sign is still just these things. I don't have to do any fancy smanchy adding of things together. It's all the same. Okay. Now, remember, this is the integral I'm trying to solve for. Okay. But I don't want to solve for it when I still have integrals going on. So now that I've isolated my integral, I divide the entire thing by this constant, and then I will know what my transform is equal, okay? So my transform is equal, and now I just flip this over and multiply that times each term, right? So this is going to be s squared over 4 plus s squared times this thing, so the s's cancel, okay? So I got one s on top, this is my denominator, and I do that over here. Here the s squared on bottom, and this s squared is going to cancel, so I'll have 2 over 4 plus s squared times cosine 2t e to negative st, okay? And that's it. I'm done. This is what my transform looks like. Except, you're right, t's everywhere here, you guys, right? I need to evaluate this at t equals infinity and t equals 0, okay? It's a bounded improper integral. You got to get rid of the t's, so it's only in s's. So let's think about this. At infinity, this goes to 0. This just oscillates. This just oscillates. Obviously, the decreasing exponential is going to send this to 0 and send this to 0. Okay. At 0, sine is 0, so this whole thing is 0. This is 1. Okay, so I'm going to have 1. This is 1. So I'm going to have minus 2 over 4 plus s squared, which gives me a positive 2 over 4 plus s squared. So now I have all of my stuff, except I need to multiply this by 3. Okay, don't forget that. That's one thing with leaving something out until the end, is you can't forget to do it at the end, right? So that's the Laplace transform of sine 2t. So if I'm multiplying that by 3, right, 3 times that thing then will give me 6 over 4 plus s squared, right? Because I did not do 3, I just did the regular transform. So that's my answer, okay? That's not my answer, but that's the last piece I need to get to my answer. So the Laplace transform of this whole crazy function that we did in 4 different pieces, I just now add the pieces together. I don't have to actually add them, common denominators, all that crap. I just say it's this plus this plus this plus this. That's it. Okay, so again, there's not a lot of extra work here. The 2t squared transformed into this function. The negative 4e negative 9t transformed into this function. The 3 transformed into 3 over s, and the 3 sine t was 6 over 4 plus s squared. Okay, we could probably switch this back around, though. Sorry, I just want to check something. I did write as 4 plus s squared. Right, so we just want to, we could switch this back around to the proper order. That's fine, doesn't really matter, okay? But I am not going to combine all these things. I'm not going to, you don't have to do that. In fact, it's encouraged for you to not do that, okay? It's actually better to keep it this way. So let's talk about some transforms of some of our basic functions. This is actually going to be super useful, and you'll see an example of that in just a second, okay? So some of our basic functions that we're going to run into, okay, are going to be things like a constant. The linear transform of a constant is just 1 over s. We saw that already here, okay? The linear transform of t to a power, in this case we had 2, is just going to be the factorial of that power over s to whatever that power was plus 1 more. Here n has to be an integer, okay, a positive integer. This is not going to work for like 1 over t squared, right, like a reciprocal function. It's not going to work for like t to the 3/2. It has to be a regular polynomial kind of power function. Okay, so for an exponential, e to the at, it's going to be 1 over s minus your exponential multiplier, I guess. I don't remember what it's called. Okay, for the Laplace transform of a sine function, okay, times some period changing value, okay, is going to give you that period over s squared plus k squared. Okay, cosine will be the same thing, but instead of k on top, you have an s on top. Okay, then we get into sinh, which is very similar to sine, almost identical, except that instead of a plus, it's a minus. Still a k on top. And for, that's right, cosh, it'll be identical to cosine, but instead of a plus, it'll be a minus, right? So these are our 7 basic functions. We can pretty much build all of our functions from here. And if we can't, then you saw how we do it from scratch, which is taking those integrals. So let's do an example from using these basic transforms. Now, let's evaluate the same exact thing we just did. Now, me talking you through it was, I want to say it was about 10 to 15 minutes of just us talking through each of these integrals, especially the first and the last one. But it took quite a bit of time. It took a lot of, it takes a lot more time to do it by hand, right? Now we have transforms, okay? So what I'm going to do is I'm going to start it off the same way. I'm going to separate each of my things, okay? I'm going to pull out the constants and just transform each function. And then I can just transform literally each function, okay? T squared means I take the power, which is 2, factorial it, and then I will write it over s and add 1, okay? The 2 is already on the outside. The next one is negative 4 times the transform of e to 9t. Well, that's going to be 1 over s minus a minus 9. Okay. Here over 1 will give me 3 times 1 over s. And for sine of 2t, well, my k here is 2, so I can write this as 3 times k is 2, s squared plus 2 squared. Okay. And then when I actually do all of this, which you probably could have done in your head because it's very simple math, right? What's 2 factorial? It's 2 times 1 times another 2. That's a 4, right? Minus 4 over s plus 9, 3s. This is 6, s squared plus 4. Do you see how much faster this was once we had these forms compared to all of the work that I did before? Okay, so let's see here, right? So from before, I had this whole page of work just for one transform. And then for the other 3 transforms, I had all of this work, okay? So for our video, 2 pages worth of work, right? Compared to literally 3 lines, right? To get the exact same answer. So these transforms, these basic transforms are going to be super, super helpful. Okay, there's a lot more of them. It's on the last page of your actual book. So we're going to get really, not super deep, but we're going to cover the basics because we're running out of time. So I'm going to do about half of chapter 7, and then we'll do just a quick run through of chapter 8, which for, again, those of you in my linear algebra class, we've already pretty much done that whole section or the whole chapter except for one section basically in linear algebra. So we're going to actually run through that really fast. So you guys have a nice snapshot of this DE class. Okay. So again, these transforms are super important. Okay. So definitely, you'll get some practice with these for this section. Let's go over a definition real quick and then we will be done. Okay. We have one more example. So a function f is said to be of exponential order c if there exists constants, so real numbers, c, m, which is positive, non-zero, and t, which is also non-zero and positive, such that the absolute value of your function is less than or equal to some exponential function, okay, for every t larger than this t. Now you might be saying, what the hell, Professor Williams, what the hell are you showing me? Okay, this is actually a very, very simple thing to explain. It's basically saying that your function is bounded above at some point by an exponential function. That's it. Okay, so sooner or later, if your function, whatever function you're looking at, will be smaller than some growing exponential, then you're of exponential order. And the order that you are determines the point where you're basically equal to that function. Okay, so again, let's think about these functions. 2t squared. At some point, any exponential function is going to outgrow this. Okay, 4e to the negative 9t. At some point, any exponential will outgrow this because it'll be positive. This is a negative. Constant 3. At some point, any exponential will have a value larger than 3. 3 sine t. At some point, an exponential function will overtake this. Okay. So now your question might be, well, Professor Williams, what if this was e to the positive 49? That would still be bounded above by some exponential. What if I had e to the 10t? E to the 10t will sooner or later be larger in value than e to the 9t. So even if this is a positive exponential, you can always find another exponential larger than that to bound this integral as t goes to infinity. Okay, that's all that this is saying. So if this is true, if you're bounded above by an exponential, then you're of exponential order c. Now, I did not paste a picture on here. I've been trying to, remember to put pictures on here whenever I see them. But I just went through the math. You can go ahead and look in 7.1 and there's lots of pictures of graphs. Just take a look to that might help you out to have an idea of what it means to be of exponential order. Okay, basically it just means you're bounded above by some exponential function, right? So let's look at a theorem, and then we have one example, and then we're done. Okay, so we're almost finished. If we are piecewise continuous from 0 to infinity, so piecewise continuous means that there are no gaps in the x direction, or in this case, the t direction. Okay, so as you're going along your horizontal axis, you do not have any point where you cannot evaluate your function. Okay, now you might have gaps in your y-axis, right? So you might have jump continuity. So you might, you know, at 5, for instance, you might get out 2. 2 might be open, but you actually evaluate at 12. That's fine, right? Because along the horizontal axis, you can always plug something in and get something out. Okay, so that's what it means to be piecewise continuous. But if you were to draw your graph, again, you would have to take your pencil off your paper in order to draw your graph because it's piecewise. Okay, there's pictures of piecewise continuous on there as well, but this is again something from Calculus 1. So if you have to review that, just go into 7.1 in your textbook and look at the picture of your example for piecewise continuous. Again, apologies for not including a picture on this video. Okay, so if you're piecewise continuous from 0 to infinity and you are of exponential order C, then the Laplace transform, I'll fix this L, right? We need the fancy L, not the regular L. The Laplace transform exists past that point that you're looking at. Okay, so before that bounded portion, right? If you're not bounded by a function before, then you cannot do the Laplace transform. So you have to do it after that bounding of whatever bounding function you would have, right? So let's do an example. Basically what this is saying is that if I'm piecewise continuous, I can do the Laplace transform, right? So, and again, I'll fix this on the right out, these last two parts for my fancy L. Find the Laplace transform for this function. So again, this function is piecewise and it's piecewise continuous because I'm open at 1 here, but I can still evaluate myself at 1 and I'll get 0 out. So there's no point where I'm not allowed to plug something in. Okay, I am continuous piecewise, right? But obviously if I plug in 1 here, I'm gonna get out 3. If I plug in 1 here, I get out 0, right? So there's a jump discontinuity. It's not a single continuous line, right? So if I want to evaluate this with the Laplace transform, I basically just do each piece separately, okay? So I'm going to break this down into 2 integrals. One for this bound, and then for this bound. So from 0 to 1, I'm this function, and from 1 to infinity, I'm this function. Now, we don't have any quick transforms for something that looks like 2t plus 1, but I could, if I wanted to, break this into 2 parts and use just a standard t, where 1 is the exponent, and then the single 1, right? Because that's what this looks like. But I didn't. I did the actual integral, okay? But I could have broken this down into 2 parts for this integral, right? I could have broken this into 2 separate integrals, and this into 1. I don't know why I didn't. I wasn't really thinking, I guess. Right? But I can differentiate this and integrate this piecewise. And so I have this piece and this piece for, right, the first term, the second term, this goes to 0. You evaluate that from 0 to 1. Okay. So I got e to negative s over 3s over 2s squared es, right? So if you notice, this is a little different because it's not from 0 to infinity, it's from 0 to 1, okay? So what's going to happen here, I want to take that back, I can't use those other transforms because the bounds are different on this integral, okay? So this is what we are going to get, okay? And so for this part, this just goes to 0 because I'm integrating a function that has no output, so there is no area underneath. Okay, so I'm really just integrating this function from 0 to 1. Again, differentiating here, taking this and integrating, and then doing my table method. So 2t 1 over s e to negative s squared, negative 2 over 1s squared e to negative s from 1 to 0. So when I evaluate at 1, I just get 3 here, negative s, 2 over s squared e to the s, and then add 0. This turns into 1, this turns into 1, and this turns into 1 as well. So I got negative 1 over s times 1 because of this single 1 here when I plug in 0. And so then when I try to simplify, I'm not really simplifying, but I am combining my like terms. Again, it looks like I have a mess up here, but this should be an e to the negative s, right? I have 3 over s, 2 over s squared, 3 over s, 2 over s squared, both e to the negative s, so there should be an e to the negative s here. So I'll fix up this sort of last slide on the write-up, but this is how you would do your piecewise function. Okay, so again, I'll fix this. This should just be an e to the negative s factor that we pulled out. And that's the only thing that's kind of incorrect here besides these fancy L's. Okay, everything else is right. So I'll fix that on the write-up. And I hope it's not too confusing for you guys. Alright, so on our next video, we will go over what's called the inverse transform, which allows us to basically go the other way. Okay, and before we go, don't forget you also have a classwork for this section. Okay, so this is your classwork. I'll let you kind of read through it. Of course, you can pause it and then write it down so that you can finish working on it, but this will be due at midnight. Thanks.